Well, welcome back again and happy May to you guys. I hope you're doing okay. And of course, we are really getting close to the end now. So in class, we have this week and next week, and basically that's it. And since you guys have been real good about keeping up with your work as you went along, once we're done with next week, you're going to be good to go because you don't need anything for the last couple days of the school year, which are officially designated for people to turn in late and missing work. Last week's quiz, for the most part, people did great on. The one question that caused some issues was number 3. And I just want to point out to you that when you're finding area with antiderivatives, anytime that you have a region that crosses the x-axis, you've got to split it up and do it as 2 parts. On this particular problem, I would have to go from -2 to 0, work out and find out what that area is. Then I'd have to go from 0 to 1 and find out what the area on the right is. And what you do is you add up the absolute values. The reason why you have to do that is that the area on the left, you technically get a negative answer because the area is below the x-axis. The one on the right, you get a positive area. If you don't split them up and do absolute value, what's going to happen is that they partially cancel each other out. And so to get the accurate answer, you treat it as 2 separate regions and you add up the absolute values. Now I'm going to tell you this week we are going to learn the last real new topic that's going to come up this year. What's going to happen next week is we're going to review a couple of key things, and while you don't have a formal final, you will have something that kind of quickly reviews all the stuff you've done in calculus so that we make sure you haven't totally forgotten things that go back to the beginning. This week, though, we're going to talk about a topic called integration by substitution. And what it does is it allows you to find the antiderivative of hard stuff, of things that you wouldn't even have looked at before. To get into integration by substitution, we're first going to take a trip back in time to when you learned the chain rule. That was a way that you could find the derivative of a composite function. And remember what you did is you did the derivative of the outside times the derivative of the inside. So like if I wanted to find the derivative of sine of x squared, I do the derivative of sine as cosine. That's why part of my answer is cosine of x squared. But then I've got to do the derivative of x squared. That's 2x. So my final answer is cosine of x squared times 2x. The reason why I threw that in there is that what substitution really is sort of the opposite of the chain rule. They're going to give you something that basically chain rule was used to find the derivative, and we got to turn it around to find an antiderivative. So one other little bit of background before we actually get into doing the chain rule is I mentioned clear back at the beginning of derivatives that there were multiple ways that you could write derivatives. Most of the time when I've done things in class, I've used the prime symbol to mean derivative. That's technically what's called Lagrange notation. Lagrange was a French mathematician that I really haven't talked much about because while he worked with calculus, he came just a little bit later than Newton and Leibniz, and that's why he doesn't get nearly as much credit, but it was his notation that we use for derivatives. What we're going to use as we get into substitution is actually Leibniz's notation. It's dy over dx, the difference in y over the difference in x. And that's going to become important to how the notation works when we do substitution. So yeah, integration by substitution, it is basically the opposite of the chain rule. And when we do it, we are going to use that dy dx Leibniz derivative notation. And what's going to happen is we will see functions that on the surface look a lot more complicated than what you've done before, but we need to be able to find the antiderivative of things like 3x squared sine of x cubed dx. Now, This is something I will tell you you can't just do on a calculator. There are actually some ways that you can accomplish antiderivatives with technology, and that's one of the things I'll actually talk about a little bit next week. But we're not looking for a number answer, we're looking for a function, a formula. This is the part that's going to have the plus k in it. And so, yeah, I can't just work it out on the calculator like I did with the area problems or the definite integrals. So the basic steps that we're going to do start by locating what we call the interior function. And this would have been like the g of x when you were doing chain rule. It's what's the furthest inside of things we're looking at. In this problem, that's going to be x cubed. Now, I always call that inner function u. So here, u is x cubed. Now, I'll formally write down later some of the things you can look for to locate those interior functions. After a trig function is a classic way that you can find it. You might also see it inside parentheses, under a square root, on the bottom of a fraction. All of those different places are ways that you can locate u. Once I've figured out what u is, what I've got to do is find the derivative of u. And when I do that, I use Leibniz's notation, so I write du dx. And I take the derivative of x cubed, which is 3x squared. So du dx equals 3x squared. Neither of those steps should really take a whole lot of time or be very hard. I just find that interior function and I take the derivative of it. The next step is to solve that derivative for du. I get du by itself. And if you look at the bottom, you'll notice what I did is I just took du dx equals 3x squared. I multiplied both sides by dx. So du equals 3x squared dx. Now, that may seem kind of dumb, but there is a darn good reason why I did that, because if you look at the things I have written on the right-hand side, they're just split up, but it's mostly the stuff that I have in that antiderivative I'm supposed to find. So now what I've got to do is substitute. This process is called integration by substitution. And so what I'm going to do is substitute the stuff that's in my original problem and make it say stuff that involves u. So I figured out that x cubed was the same as u. That's why we're going to have sine u in our problem. The rest of what's in that original problem was 3x squared and dx. Well, if you put those together, that's what du is. And so you can see I highlighted so I could see what got substituted here, but u changed into x cubed, 3x squared and dx, together those changed into du. That's why the problem I've actually got to work out is sine u du, take the antiderivative of that. Now, doing the antiderivative should be a relatively easy part, although I'm going to tell you, I noticed when I was narrating this video that I'd actually screwed this up when I was preparing it ahead of time. You should know that the antiderivative of sine is negative cosine, and that's why what I should have here is negative cosine u plus k. What I screwed up when I was doing it and preparing ahead of time is I just put cosine, I forgot the negative, but yeah, it is negative cosine u plus k. And the last step is to substitute back so that our answer has x in it. We knew that u was actually equal to x cubed. That's why my final answer is going to be negative cosine of x cubed plus k. And so again, the basic steps, I first of all find that interior function, the u. I take the derivative of that and solve it so it says that du equals something. I substitute, I find the antiderivative, and then I substitute back so that the answer has x in it. So find interior function, derivative, substitute, antiderivative, substitute back. So take a minute and see if you can do this one. You might want to even pause the video for a second first and see if you can come up with the antiderivative of cosine x square root of sine x dx. The innermost function is sine. It's underneath the square root, so u equals sine x. The derivative of that would be cosine x. On this screen, I've got a bunch of things going on. I first of all solved that derivative so that it said du equals cosine x dx. And then again, you can see that I've highlighted all the stuff that I know. In blue, I figured out that u was sine x. That's why my final problem has the square root of u. Everything else up on top there, cosine x dx, that's the same as du. So the problem I really have to solve is square root of u du. And to solve that, what I'm going to do is think about it as an exponent. We've got u to the 1/2 power du. To work with that, I add 1 to the exponent, divide by the new exponent. That's why we've got 2/3 u to the 3/2 plus k. And again, the final step is to substitute back. So 2/3 sine x to the 3/2 plus k. That's going to be our final answer. Fairly common question people have is if I've got a big, long, complicated function, how do you know what to pick for u? Like if there's both sine and cosine there, which one do you use? One thing to do is to look for a power and do what's inside of those parentheses. In this problem, x cubed plus 5x squared minus 7x plus 4, that would be the u. If you've got a root in a problem, what's underneath the root is probably going to be u. So here, 2x squared minus 5x plus 11. Something we haven't done yet, but it will be coming up here, is if you have e to a power or another number like 5 to a power, whatever that exponent is also likely to be your u. So in this problem, e to the sine x cosine x dx, my u is going to be sine x. Anything that comes after a trig function, what the trig function is a function of, that's going to be a u. So like in this problem, natural log of x would be my u. And yet another thing to look at is the denominator, the bottom of a fraction. In this problem, 2x squared plus 5x, that would end up being the u. Now, in an awful lot of problems, including all of those examples I just went through, if you figure out u, you're going to find that whatever else is in the problem happens to be the derivative of u. Real good question is, well, what if that doesn't happen? What if you take the derivative and it doesn't just automatically cancel out everything else that is there? Well, it turns out that if they're going to ask you the question, it can't be too hard to make it work out, and so we need to figure out what's going to happen in that situation. And to do that, I'm going to start with this problem. We have the antiderivative of x squared cosine of 5x cubed dx. And so we've got a problem that when I look at it, it's not impossible, but it's not the world's easiest problem either. I can hopefully figure out that u here is going to be 5x cubed. But when I do the derivative of that, I get more than just x squared. So there's other stuff involved as well. Again, the u is what's inside the parentheses, 5x cubed. If you take the derivative of that, du is going to be 15x squared. Now, it looks like there's an awful lot going on the screen, but it actually isn't all that big of a deal. What I did is, just like before, I took that derivative, du dx equals 15x squared, and I solved that for du. But then what I did is I divided in order to turn this into what I'm trying to cancel out in the problem. I had 15x squared dx, but in the original problem, it just says x squared dx. So then what I did is I divided by 15, And I got that du over 15 equals x squared dx. I've got to look at what I'm trying to cancel out and do what I have to make an expression that's going to be the same as what I'm trying to cancel out. So it turns out that du over 15 would equal x squared dx. All of that stuff that's in yellow I can change into du over 15. I can change the 5x cubed to u, and that's why what I'm going to end up with is the antiderivative of cosine u du over 15. And actually, again, on this problem, I noticed when I was recording this video that I'd screwed up the antiderivative, but I fixed that so it's correct now. The antiderivative of cosine is just plain sine. That over 15 just tags along in the answer, so I'd have sine u over 15 plus k. And since u is 5x cubed, that's why my final answer is going to be sine of 5x cubed over 15 plus k. And so again, the basic idea is that if your derivative doesn't exactly equal the expressions that are in the antiderivative, what you've got to do is find an expression that involves du that does equal what you're trying to cancel out, and then you replace that with the whole expression rather than just with du. So here's another problem. We're trying to find the antiderivative of e to the 5x power. And again, you might want to think, what would you have to do with this? Maybe pause the video for a minute, and then we'll look at the answer. And if I do have e to a power, that exponent is going to be my u. So u would equal 5x. The derivative of that would be 5, and so du is going to be 5 dx. Now, again, in my problem, there's no 5 in the original problem, so I've got to divide by 5 and say du over 5 equals dx. I replace the 5x with u. I replace dx with du over 5, and that's why I've got to do the antiderivative of e to the u du over 5. The antiderivative of e to the u is just e to the u, so I get e to the u over 5 plus k. Go back and I've got e to the 5x over 5 plus k for my final answer. And another one to look at and see if you can work out and find an answer to. So this time u is going to be what's inside the parentheses, x squared minus 9. The derivative of x squared minus 9 is 2x. So if you multiply, you'd get du equals 2x dx. The problem is there's no 2 in the original problem, so I'm going to have to divide to cancel things out. Du over 2 would be x dx. And after I do my substitution, what I'm going to get is the antiderivative of u to the 8th du over 2. Well, this is just a power problem, so I add 1 to the exponent, get u to the 9th. I divide by 9, or that's the same as times 1/9, and that's why I end up getting u to the 9th over 18 plus k. And if I go back and I substitute in what u was equal to, our final answer is going to be x squared minus 9 all to the 9th power over 18 plus k. Got 2 more problems we're going to do as examples. Here we've got, let's do the antiderivative of x cubed times 7 to the negative x to the 4th dx. Now, if I had tried to give you this problem, a section or two ago, you would look at this and probably run away scared because it's just a weird and nasty looking problem. But it turns out it's not that big of a deal to do with substitution. So again, if I've got exponents that have stuff in them, that exponent is going to be my u. So here u is negative x to the 4th power. If you do the derivative of that, you get negative 4x cubed. So du is negative 4x cubed dx. I go back and I look at the original problem and I realize, yeah, there's no negative 4 there. So what I've got to do is divide by that -4, and it turns out that du over -4 would be x cubed dx. When I do all my substitutions, we're going to get 7 to the u du over -4. One of the rules we learned when we first started doing antiderivatives, you very likely may have forgotten by now. But if you have some number other than e to a power, the antiderivative of that is that same number to the power over the natural log of that number, which is why the antiderivative of 7 to the u would be 7 to the u over natural log of 7. Notice what I have written down here is 7 to the u over -4 ln 7. The -4 again just tags along in the answer, and of course you do put the plus k at the end of it. When I go back and I substitute, my final answer is going to be 7 to the negative x to the 4th all over -4 natural log of 7 plus k. Finally, the last of the example problems we're going to look at. This one is asking us to find the antiderivative of tangent x dx. So in order to do that, we're going to first of all realize that tangent is just the same thing as sine over cosine. And you might look at that one for a minute and see if you can figure out what you would do for the antiderivative of sine x over cosine x dx. So a couple things with this one. I've got a fraction, and when I have a fraction, a lot of times the u will be what's on the bottom of that fraction. And here the denominator says cosine x, so u equals cosine x. The derivative of cosine is negative sine. This time I did it right with my negatives. And that means du would be negative sine x dx. Well, in the original problem, I've got sine x dx, but I don't have a negative. Which is why when I do the substitution, I'm going to have to toss in a negative. I'm going to have 1 over u du, but there's going to be a negative because of that negative that I have in the problem. Basically, sine x dx would be negative du. Well, the antiderivative of 1 over something is natural log. That's because if you tried to use the power rule, this would be where you'd end up with something to the 0 and have to divide by 0. And instead of that, it is natural log. So we're going to get negative natural log of u plus k, or in this case, negative natural log of cosine x plus k. Now that is a lot of stuff to keep straight in one place, although the real topic is figure out your u again, find the derivative, work with it until you can match up the things that you need to cancel out, substitute, find the antiderivative, and then go back and substitute what u was to find your final answer. That's pretty much what we do with substitution. You're going to get some practice with that on a worksheet, and this will be one more time that you're going to end up doing a handwritten quiz that you'll end up emailing to me. There's just not really a good way to do multiple choice questions on problems like the ones we're doing here. Yeah, next week we're not really going to do anything new. We're just going to kind of tie things together and make sure that you're good with what we've done. I've been honestly kind of amazed at how well you girls have done this spring. And, you know, that's really a compliment to you and how smart you are overall. But we're going to leave it at that for this week. Wish you well, and we will talk to you one more time a week from now.